Greetings and welcome back. Now I would like to walk you through the slides and explain different terminologies, different aspects of neural networks. We do not wish to go deeply in the mathematical understanding of neural network. We briefly touch it. There is going to be an example that is going to help us understand how the function works. But generally speaking, the main idea here is to actually familiarize you with the terminologies. So neural network classifier, part 4 of session 7, that is going to be on predictive modeling and classification. As you have seen in previous recording, we have different parts of the basically neurological system that is going to be working together. So we have dendrites, we have the nucleus, we have axon, we have basically the connection between one of the cells to another one. This is going to be, these are going to be the synaptic terminals. This is considered to be a synapse where the signals are going to be approaching. And so that's the overall shape of the biological system. Basically, artificial neural network is a type of machine learning that is going to be mimicking what the biological organism do in the brain, typically. The human nervous system contains cells which are referred to as neurons, and connected with the use of axons and dendrites, and the connecting region between axon and dendrites are referred to as synapses. Generally speaking, we want to map this. We want to slowly model the biological system into a schematic that we could potentially remember and work with. So this system is going to be a bunch of neurons. There are going to be some sensors point. So those sensors point or the data is coming at this time. So this is a neuron, and a neuron is going to fire not all the time. So the neuron is going to fire under a specific function. The function for the neuron we are going to discuss. There are different types of functions. Some of them you have already seen in the previous recordings via the clips on YouTube. And then whatever happens, there is going to be a signal sent. Once again, you saw that in the previous recording. Please go back and have an intimate understanding of how the system works. So these are the data that is coming in. These are going to be the importance. We would call them weight. So whether I'm going to magnify or attenuate or basically weaken the signal depends on this W's. I could potentially magnify this, and I could potentially weaken this signal depending on what I need to do at the end of the day. And then I have a neuron, there is a function inside, and then there is going to be a firing. The firing is going to happen, okay? So let's begin and work with that schematic now. So this is my schematic. And there is going to be an axon. So the axon is actually here. This axon is the output of the function. X1 up to Xn are going to be my incoming data. These W's are supposed to be my weight. And here is a simple function. And the function says, let's have W1 times X1, W2 times X2, Wn times Xn. Let's sum them up. And when you get that, it's going to be whatever is inside the bracket is going to be my net. And this is going to be my accumulated input to my neuron, and there is going to be a function that is going to act upon this input. So this is going to be accumulated input. Weight of all of these inputs are going to be considered and eventually added together. You could have 1 or 0, you could even have fraction on the weight, generally speaking. Now, with the net being the accumulated input, W1, X1, W2, X2, and you sum them up. Now here, what is the function? What are the functions we are talking about that the neuron are supposed to work on? So, or behave upon or operate upon. So what is happening is this: I need to have a net, an incoming signal that is coming in, and then f of net is going to be linearly increasing. And if this is 45 degrees, obviously net and f of net is going to be exactly the same. Linear function doesn't have to be exactly 45 degrees. This is just an example. But the entire idea is that as net increases, you do have output. Your axon is actually sending the signal based on what the input is. It's not going to wait. There is no threshold involved. It's just net comes, f net goes, and that's the linear function, one of the functions, one of the many functions. Now, the other possibility is called a step function. The step function is actually mimicking one of the examples you have seen in the recording in the previous session, and that is neuron is not going to fire all the time. Neuron is going to actually collect and collect and collect, and at some point, when it reaches a very specific value, a threshold, it starts firing. So here is an example. So as long as net, so there is a horizontal line, then a sharp change, and then horizontal line again. What does it mean? Imagine that this is the threshold. This is the threshold I'm talking about. And this threshold in this figure is actually noted as E. If the accumulated value, input value, called net, is less than or equal to E, for example, about the equal sign, you can choose what to do, but less than or equal to E, neuron is going to be silent. There is nothing to do. The neuron doesn't do anything. It's going to be off. Now, if the accumulated input called net is going to be more than E, then the neuron is going to fire and it's going to turn on and send a signal. Okay, you could potentially say this level off is going to be 0 and this level on is going to be 1, but they could also be some sort of an offset. We will talk about offset in a moment in some of the schematics. So this is a kind of an example that you have seen in that recording, the previous recording, where there has to be a threshold. Before the threshold, neuron doesn't do anything. After the threshold, it fires and sends a signal to the next, basically as the input to the next neuron. So keep in mind that the output of this function potentially could be the input, one of the inputs of the next stage of neural network. So you need to keep that in mind. It's not going to be necessarily as simple as you just saw. Now, sigmoid is another function, and in the sense of sigmoid is that it is reacting. F of net is actually reacting to the net. So if it is 0, f of net is going to be very insignificant, and as soon as net is accumulating, f of net is going to wake up, and then it's going to go through a phase, and then eventually you're going to see the output going to be settling down. The function for that is written in this part. You don't have to remember this. It's just a matter that the way it's going to behave is going to behave like a continuous sigmoid function. This function is famous. You have seen that in our previous recordings in the past. It's called Gaussian function. You do have a standard deviation. You do have a mean value. So the mu is the mean value, and the net minus the mean. And this function together is called Gaussian function. And what does that mean? It means that when the net is very small, f net is 0. When the net is very high as well, f net is 0. However, when the net is around the average point, the function is going to fire. The neuron is going to fire. And it's a summation of the output signal is going to be continuous. That's what it means. So the shapes are really simple for us to understand. Now let's get together and understand a few terminologies. Again, we are not going to go deep inside. We are not going to be involved with mathematical notations and all that and solve the problem. As a matter of fact, this could be done iteratively. This could be done as in optimization. We are going to talk about the optimization in a moment. The task of this presentation is not to basically attempt to solve that optimization problem, rather to help you see how the neural network system actually works. So a symmetric, fully connected network, as you can see, these are going to be my neurons. I do have input coming in. So this neuron has a bunch of input, possibly. This neuron has a bunch of input. And then these neurons are going to be connected to upcoming neurons. So this could be, they could potentially provide input. And keep in mind, this is an input. This line, which has a 1.9, is an input to this node. This node that is inside, intermediate, and hidden from the view could potentially provide an input to this neuron. And then at some point, we are going to have just one output node. What do we see? We see input node, but potentially we could say even we could possibly interact with the neurons, neurons that are at the input stage, and then we have a neuron that is at output stage, and it's going to be an output node that we are going to observe as the outcome of all the interactions. Now, if you take a look at this, what happens is that every node is connected to every other node. So you have this node connected to itself, this node connected to itself, and so on. This node is connected to this node connected to this node connected to this, and vice versa. Everybody is connected to everything, and then you are going to have an output node. So that's called a symmetric, fully connected network. Obviously, the connection could be positive, excitatory, negative, inhibitory, and then irrelevant could be zero, meaning the line even doesn't exist between the two neurons. Let's get to know another type of structures. Once again, these are the terminologies that you're going to be hearing about as you move to the advanced courses on neural network. Symmetric, fully connected networks. Now, what does that mean? It means that these two are not sending signal one way. So in the previous one, the neuron has to send a signal here, and the weight was 0.3, and this neuron was sending a signal back here, and the weight was 0.8. That was a symmetric, fully connected network. In this case, it's slightly simpler, and that is these two are actually interacting and engaging and submitting information basically with the weight of 0.3. It looks as if, so for example, if I wanted to explain what the bidirectional line is going to be, you have a water hose, and you have a water hose, and you have water going from the head of the water hose up onto the garden. That's going to be a single direction. But at the same time, if you have water onto the, basically, if you have one water pond on one end and water pond on the other end, and then you open up a canal between the two ponds, the two waters are going to move. It may not even be visible to your eyes, and they are actually going to interact. It's really as simple as that. So you do have some sort of an input node again, and then you are going to have some output node once again. You could even have multiple output nodes in here, but there are going to be some hidden nodes anyway. And this one is going to be symmetric. The reason we call it symmetric because this one was 0.3 and 0.8. This one was 0.01 and 3. This one was minus 0.5 and 0.1. So that's why we call it asymmetric. Here we are going to call it symmetric because the weights are exactly the same, okay? Neural network architectures. Now that we have understood the connectivity, we want to move ahead and actually slowly move toward the pictures and images you have seen on internet discussing neural networks or artificial neural networks. We have a layer network, and in layer network, you could potentially have a layer here. This is one layer, layer 0. This is layer 1, and this is layer 2, and this is layer 3. Layer 0 often is called input layer because it's actually interacting with the incoming signal. Layer 3, or whatever the last stage is called output layer because that's where the output signals are actually generated. And whatever is happening inside, we are going to call them hidden layers. Now, in this case, if you take a look, this one is connected to this as well. This one is connected to this. This one is connected to this. And as you can see, these two are actually connected. So kind of there have no connections from nodes in layer I to those in layer J if I is greater than J. So I don't have a connection in this example. Nodes are partitioned into layers and that have no connections from nodes in layer I to those in layer J if I is greater than J. So for example, this may be this is not the right description, because as you can see, we do have connection here and we have a connection here. So this statement needs to be revised. But the entire idea is that this is a layered network. So we have an input layer, we have an output layer, and we have hidden layers in between. Now, acyclic networks, connection is allowed for any node in layer I and layer J if for J greater than I. So if you take a look at this, this could potentially be, if you take a look at the differences, you can see that interlayer connections are removed. So this one and this one are removed here. This one and this one are removed here. And if there was any interconnection in the layer itself, they have been removed. Everything else is left basically the same. Once again, input layer, output layer, and hidden layer. So again, these descriptions that you see as a text, I would have to revise them and make them more precise to be reflective of what you see on the right-hand side. But generally speaking, we have layered networks and we have acyclic networks. Feed-forward networks, in the feed-forward network is allowed from a node in layer I only to node in layer I+1 that is most widely used in architectures. The one that you see on the internet, the one that you see in research papers. What does it mean? If you take a look at this one, you can see that I have, for example, layer 0 and layer 2, they are connected. I could potentially have layer 0 and layer 3 connected, generally speaking, if I wanted to have all connections in my schematic. But here, no. It is always connected to the immediate layer and nothing further, doesn't go as far to the next. So this one is connected to this, but this layer, sorry, this is input, this is input. This one is connected to this, but this one is not connected to this. This one is connected to this. This could be connected to this. This is the upcoming layer. This is the future layer. The connectivities are actually allowed, but this one is not connected to the one after the future layer. This is not connected to this one. This is feed-forward network, and as you can see, there is a little thing here, and these are called bias input. So you have X1, X2, X3, X4, up to Xj that are coming in, input data. And then you have a bias system here, and they don't change. They could be 0. Irrespective of the betas, if you have 0, then this is actually as if it doesn't even exist. There could be positive, there could be negative, and these values could be huge. They could be small. We are going to see some examples in a moment, but they are supposed to be acting like an offset, acting like a DC, and they never change. Irrespective of what the inputs are, they never change. And then you are going to put them in, and then you are going to get to class 1 and class 0. What are they? If you remember, we talked about yes and no many times. So this is going to be class 0, for example, no, and class 1, which could be yes. And these are going to be the incoming data. You need to make sure that these are expressed in number, because a neural network doesn't necessarily work with the categorical data. So if you say red, you need to represent it with a number. If you say green, you need to do that. Or if you say higher level or lower level, or if you say youth and young, senior and middle age, you have to represent them by number, because neural network works on numbers. Of course, you already know what your dictionary is. So when you actually map it to 1, for example, red to 1, you already understand what 1 means in the entire process. Neural networks have been used successfully in a large number of classification tasks, recognizing printed or handwritten characters. Very famous one. You could easily find many research papers and many topics on this. Classifying low application into credit-worthy and not credit-worthy groups. Analyzing sonar and radar data to determine the nature of the source of a signal. You could potentially use neural network for clustering. You could potentially put, as we spoke of clustering in the past, those that are inside this class and very similar, you want to put them together, and you don't want this to be similar. You don't want this to get confused. So you're going to actually make sure that this similarity is pronounced in your clustering approach. We have spoke of that in the past. Now, function approximation is one of the application of neural network. You have a function, and this kind, when we talk about function here, we are talking about functions of complexities, potentially multidimensional, and then the idea would be how do you handle the basically creating a function that is going to be similar or close enough to mimic the behavior of an existing function. Vector quantization is an interesting topic. We do not cover much on this one. What we are going to do is that if you have the whole of your solution space, you're going to divide your solution space into Voronoi, and then these are the regions. The Voronoi region, this is one region. Voronoi region, that's another one. Voronoi region, that's another one. And then you are going to represent each Voronoi using a code vector. So you can see this red one, these red ones are actually supposed to be the code words. And then any other vectors inside the regions are somehow are supposed to be tagged by the code word. So it would be best, as you can see, we spoke of K nearest neighborhood in the past. We would like these to be as similar to the code word as possible. So we want these to be close to the center point. This is not necessarily center of the region. As you can see, this is not a center of the region, but this is where you could potentially say your cluster could potentially take form. And the future vectors could potentially land here and stay, still they be associated with the code word that we have in this region. So vector quantization is one of the application. The other application is neural network. We have two types of, and pattern association is extremely common. We use that on a daily basis. We always say yes or no, good or bad, like or dislike. We rely on judgment based on patterns we have had in the past. Those are quite challenging to computerize, but there are easier things that we can computerize and explain on this slide. One of them is called auto association. If you take a look at this image is a simple image. And when you take a look at that as a human, and once again, we should be quite aware of the difference between human and computer. And you need to remain conscious about that difference. So if you take a look at this, I could argue that this is an F. I could argue that this is kind of a T. But if you imagine that these components are taken away from the picture, you're actually going to rebuild the image, and the image is going to be an E. So an E with the short handle in the middle. So auto association means I want to reconstruct the image, the exact image. I'm not going to do any middle person in the process. I'm not going to guess anything. I'm trying to establish a rule book by which I can actually resurrect this image from pieces of it. That's called auto association. Now, hetero association is different. Hetero association is akin to, if I ask you banana, if I talk to you about banana, what's the first thing you might think of? The first thing you could potentially think of is going to be a monkey, because monkeys eat banana quite often, right? So this is called hetero association. There is a middle person in between that is going to help you to go to do the mapping. So I'm talking about banana, and your brain takes banana and maps it to the monkey. So that's what it is. So if I talk to you a banana, the second person could potentially come back and say monkey. So if you take a look at this, in the auto association, I know this is very similar to E, but in hetero association, I'm going to say this is very likely similar to this. Why? There was a middle person here. and we didn't talk about that middle person, and that's why it went into this outcome. So this is hetero association. Okay, forecasting is a very common area where neural network applied. As I said, neural network by itself is just we are just touching the base, the surface, and it is the foundation of a huge segment of machine learning. Day and day, every hour, you will see publications popping up on the internet. Majority of them are neural network and the variations of neural networks, ANN, CNN, and all of that, even LSTM, long short-term memory, LSTM, all of that depends on neural network. We don't want to go that deep. We simply want to touch and get you familiarized with the application. One of the things that you could potentially use in a stock market is neural network. For example, you could potentially take a look at LSTM in neural network, which seems to be rather significantly studied and investigated in recent years. How the neural network works. So if you take a look at these pictures, the schematic we had, this is actually too large for me. Let's go back to my very simple model that we had. So this one. So imagine that there is an output. I have, as you know, we insisted many times that you're going to divide the data sets into a number of baskets. First basket is called training set. The second basket is called test set. And the third basket is called validation set. Usually we call validation set as unseen set. So you need to remember, many junior data scientists get the validation phase wrong. So we have a test set, we see that. We train the neural network on the test set. Then we have a train set. We are going to see how good our neural network is on a train set. Both test set and train set have been seen by the algorithm. And then we want to validate. We want to take a look at tomorrow. Tomorrow hasn't come yet, and we would like to see whether the neural network we have is going to be effective for tomorrow investigation of the stock market. Tomorrow data is called unseen data. Validation phase is about unseen data. If you give, if you make that validation phase, validation set seen by the data, that is not validation phase. You simply brought the validation set into the fold of test set or train set. So please keep in mind, it is a significant mistake that many of us data scientists do, that the unseen data is completely unseen. And the algorithm or the model, whether it be neural network or anything else, have never seen the data. That's the important part. Now, with that being said, I'm going to start basically designing my neural network. And how does it work? This is computer approach now. This is not biological approach. In biological, the complexity is humongous, tremendous, and we don't want to go into biological learning that is in your brain, the cells that are learning in your brain. So there is an output, and for a specific event, say x1, x2, up to xn, an event we spoke of many times in the past. For a specific event, we are going to say that this is going to be a yes, or 1 and 0 as classified no. So 1 classified yes, 0 classified no. So 1 and 0, again, we are going to talk about numbers. So even if you have any event, your events need to be first mapped into numbers, and you need to keep a record of your mapping first. So what do I do? For this one, I'm going to go and randomly select W1, W2, Wn. I'm going to just assign them randomly out of blue. And then I'm going to take a look at this output. And when I take a look at the output, I'm going to do, for example, the sigmoid function. Or maybe instead of, I could potentially do a step function. Let's do a step function, which is very easy. okay? So I'm going to do a step function, which is 1 and 0, right? So I'm going to assign W's randomly. The input doesn't change. W's are going to change because obviously they are yet to be known. I just set them randomly, and then the output is going to be an accumulation. This accumulation, this sum function is very easy to do. And then I'm going to watch it against my step function, against my threshold, in this case, threshold E. And if it is less than threshold E, I'm going to say it is 0, means no. If it is 1, means yes. But you see, in the table, I said train set. When I said train set, I mean the data is already investigated and the input is established, the output is established, classifier have done basically the mapping has been done to the target column already. We already know it's going to be yes or no. It's not something we are going to wait and classify. No, it's already known. This is a scene data. So the data is here. I'm going to apply random W's, and then I'm going to take a look at the function, a summation, as simple as that. And I'm going to actually check it against the threshold. And if it is above the threshold, 1, yes. Is below the threshold, 0, no. But listen, what happens if for that specific scene data, you classified it as yes, but it was supposed to be classified as no? The table, the data set that you started from, the adventure, tells you that for this specific set, for this specific event, you are going to give me no, but you gave me yes. Therefore, your function needs to be rehabilitated. And the way we are going to rehabilitate that is we are going to go back and say, oh, maybe I should change W2 slightly and change it smaller. Maybe I should increase Wn a little higher. Maybe I should reduce W1 a little lower. I'm going to calibrate my W's. And as I calibrate the W's, my output becomes the 0 I wanted. Hooray! You got one event correct. One event correct. So far, so good. But the problem is, as soon as you change the event, you need to examine the output again. The output may misclassify. And as it's going to misclassify, you don't like it. You want, obviously, the output to be classifying as best as it can. This is a scene data. And you're trying to learn on W1, W2, Wn so that for the second event, you get it right. Okay? You see that this has been misclassified again as a yes. You need to go back and adjust it. You're going to go back and play with W1, W2, Wn, maybe one at a time, maybe a couple of them at a time. Again, you're going to calibrate, and bravo, you got it. Then you're going to go for the third event, and then you're going to check the output. It is already set, so you don't have to touch W1, W2, Wn. You go for the fourth event in the test, in the training set, and then you see that you need to do adjustment. You do adjustment and everything else. By the time you finish the training set, you could say, from 1,000 events, I was able to get W1, W2, Wn with all the calibrations that I have done. And then I was able to classify for scene data, for training set. I was able to classify 99% of them yes, 1% no. We talk about the evaluation of these numbers later in this presentations, in this PowerPoint presentation. Modeling and classification PowerPoint, predictive modeling and classification, right? But here it is. You will not get 100% accuracy. You will get 99% classified correctly on the training set, 1% no. So if you have 1,000 rows, what does that mean? It means potentially 10 of the events you are going to classify them wrongly. Not bad, you would say. You would say, I can live with 99. I can live better with 99.99%. I can live better with 98. I could live 98. I can take it. 97. I can take it. 90%. I can still live with that. But 85, 80. Maybe you're actually losing the accuracy we are looking for. You want to be as close to 100% as possible. Is it possible? Most of the time, no. Is it a bad thing? No, it is not. Because you're going to say, listen, from 1,000 events, I was able to get you 999 events correctly. And just one event is not done correctly. That actually would be perfect in my domain. If you got 99.9% accurate and only 1%, 0.1%, 0.1% incorrect, this is gold. This is gold in data scientists. So you do have some errors, but you are going to say, listen, 900 out of 1,000, listen, 900 out of 1,000. I can live with 900, and then I can handle the remaining 100 up to the 1,000, the remaining 100. I'm going to handle it differently. We will talk about that later. So your error function is going to be potentially, so your accuracy is potentially going to be less than 100%. With that being said, now you're going to move into what we call the test set. The test set, obviously you have divided the training set and the test set. You could say large training set and a small test set. You could say a half-half if you wanted to divide. You could say a small training set and larger test set. We don't want to do it that way because we want the system to learn as much as possible. And often the future, the prediction, is not really long. So I would say, let's do a large test set and let's do a small a large training set and do a small test set and then worry about the validation in a moment. So we have done the training set, 1,000. Now I'm going to give you 100 test set, 100 event in test set. Now, did you achieve 99% accuracy in the previous one? Did you? Did you achieve 90% in the training set accuracy? Did you? No, the question is, when I give you the test set, do you maintain the same accuracy or not? Remember that the test set is partially called unseen. As soon as you feed it into the system, of course, it's going to be seen now. As soon as the data goes into the system, the data becomes a seen data, observed data, seen as in S-E-E-N, okay? But you are excited. You said 90% accuracy. You said 99% accuracy. If I give you the test set, and it's a small, right? This is the training set, and this is the test set, and I gave you just a test set, would you maintain 99% accuracy or not? If you do that, that's golden. I tell you one thing. If you get 90% in the training set, 90%, I lowered my threshold, 90%. And in the test set, you maintain 90%, you did very good. Because often when you give the test set to the system, your accuracy is going to drop from 90% to 80% because the data has never been seen by the package, by the network. So you're going to scratch your head and you're going to say, listen, now that we have seen it, now that we have observed the test set, let's fix it. Let's see where we made a mistake and fix it and make it a better, better combined results, combined of training set and the test set. Once again, you begin calibrating your W for every event of your test set. And then you take a look at the output value, and then you take a look at the function you have. The function you have is supposedly a step function, and you're going to fire or not fire and everything else. You go through this, and in the past, your test set gave you 80% accuracy. With the calibration you did altogether, instead of 90% you had in the training set and 80% in the test set, when you combine them together, you're going to say, okay, I got 88% for the combined set, which was 1,000 plus 100. That would be 1,100 events. So you've got 88% accuracy. This is good. This is very good. Then I'm going to give you the validation set. The validation is unseen. The validation is application of the neural network in the field, in the real-time domain. I'm going to give you unseen data, never observed before, and I'm going to give it to you. Here is the sad part. While you might have 90% accuracy in the training set, and eventually you got down to 88% when you combine the training set and the test set, the sad part is that when you feed the unseen data, your accuracy drops again and occasionally significantly. So you got 88%, you were celebrating on the street that you got 88% accuracy, then the validation set comes in and your accuracy drops to 75%. Should you be upset? Not necessarily. Keep in mind, we are talking about millions of lines of codes, millions of lines, millions of rows in the data set, hundreds of columns in the data set. So 75% accuracy, I'm actually happy with this. As a matter of fact, if you apply neural network to a stock market, and if you get 51% accuracy, potentially you're going to become billionaire with just 1% difference in the unseen data. So that's the difference in the data that you have never seen before. So if your 95, 99% accuracy drops to 55% in the unseen data, I think you should celebrate because it's unseen. The network never touched it. The network never saw it. And therefore the calibration never happened. But obviously we thrive to have better results in the validation phase. We would like to have a validation phase of up to 65%. Forgive me if I say that, maybe 78%. I want this to be that high. And there are reasons behind this, and there are ways to fix that. First, to fix that, and there are ways to take care of those errors and misclassified components elsewhere. We are going to actually take care of that in a hybrid fashion down the road. Okay, so with that in mind, we spoke of what is happening with the cell itself. Okay, with the network itself. Let me go back to this. Now, I spoke of the output of your neural network having an error value. So the error could be potentially between a decimal value versus another decimal value you had in mind, or it could be potentially just be a binary such as 0 and 1, and that's going to be your error function anyway. So there is going to be a loss function, and that loss function is the reason I go back and calibrate my W. The loss function is very important to me. The loss function is the measure of what you observe at the output and what you expect to be because of the original data set. The data set is a seen, observed data set. And the loss function or the error function is, listen, I've got 0.8, it's supposed to be 0.9 based on my available data from the field. So 0.8 and 0.9, what's the error? 0.1. And we are going to calculate that error function. So the error function is extremely important because that error function is going to impact the way you calibrate the W. And you need to calibrate the W and then get the network as best basically fit as possible, okay? Neural network objective is to minimize the loss for a neural network by optimizing its parameters, Ws. The loss is calculated with the use of loss function. And the loss is calculated by matching the neural network output with the actual output, the target value. Then we are going to use what we call gradient descent technique to basically manipulate the W. We talk about that very briefly in a moment. I want you to be aware of different types of error function. We have a famous one called mean squared error. The mean squared error means take the error. So when you have 1,000 events, you are not going to dwell on one event only. You have 1,000 events, you need to find what is the error when you have 1,000 came to your network. So you're going to have 1,000 events, you're going to have 1,000 outputs, you're going to have 1,000 or actual output, you're going to calculate the actual output and the neural network output, and you take it to the power of 2. You don't want to bring in the negative bias because of some points above or below the value, making them negative and positive. So you're going to take them to the power of 2. You're going to sum them up, and then you're going to divide it by n. That's one way of looking at it. There is another one which is called Euclidean distance. We talk about Euclidean distance in a moment. Okay. So D in this case is the desired output vector, and O is the actual output vector. So that's what the notation stands for. Typically speaking, in many of our algorithms we have used in the past, we intend to continue using it. Euclidean distance is extremely famous, extremely popular, and the way it is doing that is to the power of 2 and then 1 over 2. So it's a square root. So a square root of this distance to the power of 2, you sum them up. Now, if you take a look at this with Minkowski norm, the Minkowski norm is the same, similar to Euclidean distance, except that this k could be 3, this k could be 4, 5. If this is 5, 1 over 5 is going to be the way you take the root function. Okay, so you're going to take this to first of all, you're going to put absolute there because you don't want to bring negative value into the process. You want everything to be positive. Do not cancel each other out. That's what you want. And to the power of 5, if it is odd, of course, you don't want that negative to be magnified. And then 1 over 5. To the power of 6, you don't have to worry about it because power of 6 is going to take care of that negative impact if there is any. But all in all, we want this value to be positive. That's what we want. Okay. And Manhattan distance is, you're going to take the distance only. You don't have to take it to the power of 2 and 1 over 2 to the power of 5, 1 over 5. It's just a simple distance in an absolute term, Manhattan distance. You need to be quite familiar already with these functions, and these functions are going to be utilized for neural network and many other algorithms we have in this class. The entropy function, as you can see, we could potentially talk about entropy, very simple to what, very similar to the entropy we discussed in the past. You're going to get the log of the actual value, and then the D is going to stand for the desired value. So we are going to do basically calculate the entropy. Now, what is gradient descent? Gradient descent, once again, we are trying to explain them. We are not going to formalize this. We are not going to put the formula behind it. We are going to just talk about what the gradient descent means. I want you to, for a moment, think that you are on a top of a hill. You went sightseeing, you went into that open area, perhaps you have had some mountain or perhaps a small hill top you had been on top, and then you want to come down. You have a good shoes, by the way, and you intend to come down. And the way you are going to come down is this. You are going to put your feet, your first foot, right foot, to the front. Your body is going to sense the steepness of the slope of the hill. You're going to take your left foot and take it to, and put it at front of the right foot. The steepness is now quite obvious. Then you do this all the time, and as you go through this process, you don't want to run. You don't want to run from the top of the hill and then basically dragged down by the gravity. You don't want that. You don't want that, because what happens if you have a hilltop here and if you have a hilltop there, and if you let the gravity take you down, what happens? If there is a small metal ball on top of the hilltop, and then you let the gravity take it. So remember, metal ball doesn't have a brain. Metal ball doesn't have a control mechanism. It doesn't have a brake. Put the metal ball on top of the hilltop. What happens? The top of the hilltop, and then the metal ball goes down. And since there is no brake mechanism and there is no control mechanism, the metal ball is going to go down and then come back. So it's going to go, come back. You don't want that. You want to come down. You don't want to go on top of another hilltop unless you want to. So that's, you want to just come at the bottom base of the hilltop. That's where your camp is. You want to have a decent tea, and you want to have a cup of tea and a biscuits maybe at the base of the hilltop. You don't want to go to the next hilltop unless that's your purpose, of course. But the gradient descent is actually this. So it says, listen, I'm going to sense the steepness of the hilltop, the slope. And if it is a steeper, I'm going to move slower. I'm going to put on a brake, and I'm going to make sure that I'm not going to accelerate based on gravity. That's called a gradient descent. We are going to, gradient means tangent. We are going to actually sense the tangent, and according to the tangent, we are going to come down. And we also would like to actually apply brakes. We want to make this, so maybe while you're on the top of the hill or on a hilltop, you could potentially take the distance between your right foot and the left foot could potentially be huge, right? But as soon as you feel the steepness of the slope, the distance between the right foot and the left foot becomes smaller. So according to the steepness of this slope, you are going to put the 2 feet closer so that you can control it. That's the way gradient descent works. And at the end, we would like you to settle down at this point, for example, the global minimum or even local minimum anyway. The same thing is true if you inverse this, parabola. If you inverse this parabola on top, what happens? Well, you're going to sense the slope and you're going to put your feet on. Since you're sensing the slope, the steepness of the slope, you can see the resistance. Gravity is pulling you down. Your intention and motivation is going to go on top of the hilltop. So you need to put a lot of energy and try to take perhaps larger steps or smaller steps depending on the steepness of the slope. And then if you feel safe, then you're going to have a little larger steps. If you don't feel safe, you're going to make it the steps closer. That's what the gradient descent, gradient ascent is. This is called gradient descent, and gradient descent means let's go to the bottom of the parabola, okay? Single layered neural network. We spoke of the layered neural network in the past. These are the input. You have only output layer, and each one of the output layers is going to generate an output signal. So as you can see, this is one cell, and you have 3 inputs, all of them interacting with the cell, and 1 output. This is another cell, and these 3 inputs are interacting with this and another output, and the same goes here. You might say, listen, my input doesn't actually interact with this. That's fine. You can simply assign 0 to this weight, and this weight is going to vanish. Of course, you don't want to let it go all the time, because you never know. During the optimization process we spoke of, we could potentially come back and change this 0 to something non-zero. So that's what it is. So speaking of the gradient descent and speaking of the output, I think I might have rushed on this. Remember, we said that you are going to take a look at the output signal, and then you're going to say how far you are from the actual output, and then you're going to decide. That's the steepness of the slope. If you are close to the actual output, so this is your observed output, your desire, your basically your value that you are going to observe, and then you have a desired value, or in this case the actual value, and you see that the error is very small. If you want to calibrate these, you are not going to calibrate this with huge change. You're going to calibrate them with a small amount, because it's already close to the actual outcome. You don't want to overshoot this. You don't want to overshoot the actual output. So you're going to actually calibrate the W in the small amount. Now, if the output, the observed output and the actual output has a huge difference, for example, observed output is 0.5 and actual output is 1.5. That's a huge difference. If it is a huge difference, you might introduce a rule for calibration where you are going to actually change this W significantly. That's like the steepness as we spoke of, right? And you could potentially change this significantly so that you can potentially catch this. Again, there has to be rules, And from one sets of rules to another sets of rules would be the approach distinguished by research papers. One person is going to say, this is the way I'm going to change W. Another person comes and says, and this is the way I'm going to calibrate W. And all of them are researchers. And all of them come to a different error function. Their error function could even be very close, but they are going to actually classify perhaps as close as they can, but some of the events are going to be classified differently, right? So let's get back to this slide. This is a single layer. This is a single layer input, and then you have multi-layer neural network. In the multi-layer neural network, you're going to have hidden layers. And then this is the output layer, and this is going to be input layer. This output layer doesn't have to be one. You could potentially even have 5 output layers, much similar to what you saw on top. Because remember, all of the outputs of this layer become the input of this layer, the output layer. All of the output of this layer becomes the inputs of this layer. So you need to see the connectivity. Before I go to the next slide, I just want to tell you that the neural network is not new. It is actually more than a century old. The reason it didn't catch fire was because of the computational power we didn't have. Then slowly the microchips became quite powerful. You could do trillions over trillions of operations per second on a single microchip, and it became feasible computationally to do it. Why? Because if you go back to the single layer and single output, the fact that you're changing only 3W, calibrating 3W, is going to take a huge amount of time. If you were pre-2000, potentially before your birth time, if you are 2 decades old only, it was extremely difficult for computers of the time to go and manipulate and calibrate these Ws, and then for 1,000 events. It would have taken them possibly a couple of days, a couple of weeks, a couple of months, if the algorithm was correct, and that was not attractive. Then the computational power became quite nice, quite significant, and then there, when you put them in, you could potentially see the improvements. Open execution time, something that was only done about 1 month's execution time pre-2000 is going to be done in a couple of hours now, maybe even a few minutes today, with the computational power that we have. Okay, so that's what this one is. That's what this one is. And that's why it became quite famous and quite widespread in the community, in the scientific community, that we want to use a neural network. And another thing that you need to be aware of, the more hidden layer you have, the more time it will take to optimize, because you're going to optimize these Ws, you're going to optimize these Ws, and these Ws do not have direct contact with the primary input. They have contact with these, and they could potentially be generating and firing wrong signals anyway. And you're trying to calibrate according to wrong signals, and that's not pleasant. So you see, the more hidden layer you have, the longer it would take for the execution time to move on, okay? Again, this is a simple step function. Often we note, this is the notation, a very nice notation. This is the neuron. This summation means I want to sum up everything at the edges, as you can see, touching my my elliptic or circle. These are my inputs, the input data, and this is going to be my output. Okay. Now I do have a biased neuron, so keep in mind this could be +1, it will be -1, this could be 0. When you put it 0, effectively whatever h is going to be has no impact on it. And if it is large, it's going to have a huge impact on your result. But generally speaking, you have a step function, and a step function, you need to have a threshold. Once again, you're going to see the output. For every event, you're going to see what the output is. You need to go back perhaps to calibrate. And then the next event, you go to the output, you need to calibrate, and you calibrate them one at a time perhaps. You see, that's why it takes a huge amount of time. This is a kind of a mathematical notation where we are going to actually say the summations of x's and y's, w's, that's the summations. And if I wanted to actually note this, this is an inner product. This is an inner product of vector w, the weights, and vector event x. So that's what this one is. This inner is a scalar product or inner product. I encourage you to take a look at the remedial recordings, and that is explained how it is. And if you, even if you don't want to, this is actually a replacement of the inner product. So that's what it is. And the sine function, this is going to be the function that is going to actually apply itself through a threshold, and this is going to be a step function. This example is important, and I want to discuss that in the next recording.